recording? Recording. Okay, good. Thank you for reminding. So what we did last time, we learned how to find, using derivatives, local minimum, local maximum, using sign line. If you missed my last class, well, that's sad, because that's exactly a very important thing, and I'm very good in explaining that important thing. We sketched the graph of the cubic function, and we found local maximum and local minimum. How? Using first derivatives. This is the picture I copied from the previous class I gave you 2 weeks ago. This is exactly what the duck was doing. Calculus 3. Yeah? Yes? Yeah, come. Can you sit here in front? Are your friends coming?
No, I'm sure.
Yeah, then sit here, please. How come you're late for your own exam? Like, come on.
I couldn't find the place.
So, please write, actually, you don't have to write the official definition, but what we did last time was exactly the first derivative test, because we used first derivative sign line to, you don't have to go to scratch paper. Do you have a piece of paper?
I do.
Just make sure it's empty. We used the first derivative test to figure out the sign before and after local minimum, local maximum. And we find out that to have a local maximum, derivative should be positive, and then it should be negative. That makes sense, because the original function goes up and then goes down. That indicates a hill. For the local minimum, the first derivative should be negative, and then it becomes positive. That indicates a pit. You go down and then you go up. So visually, I taught you through using a sign line. And again, this one also goes up and then goes down. And some teachers teach you to memorize from plus to minus, that maximum. Too complicated to memorize. I'm not good at memorization. But visual learners, they see going up, going down. That's a maximum. So right now, we're going to practice more examples. You guys can help me with this, and it will be good. Let's do it. More examples. Maybe you don't wow, that's a lot. Maybe you don't remember what is happening with the critical values we did, but it's fine. I will help you to review. Let's do some easy example and then a hard one. The easy one are usually with polynomials. 3x to the 4 minus 16x cubed plus 9. Find all, so usually we ask you 3 questions. That's example number 1. Let's put it in the box. A, we usually ask you 3 questions. Find intervals of increasing, decreasing. Intervals where the original function is increasing, decreasing. B, find local or relative, that's the same thing, extreme, let's say local or relative extrema. That's a synonym. English did not agree how to call it. To be honest, in Russian we call it the same thing. You guys did not agree, so it's either local extreme values or local extrema or relative extrema and relative extreme values. In English, they did agree about global one. Global is global. That's it. But you should understand, extrema means something extreme is happening. Oh, why my business just jumped? I'm selling ice cream and look, my business just jumped into the maximum. Oh, because it's July, and so on. So like it's extreme values, it means something. Or local one, minimum one. What does that mean? So I said 3 questions and then I wrote 2 because the very beginning starts with the question, find critical values. Did we do values or numbers? Values, yeah. Where the moment you see the question about increasing, decreasing, local minimum, maximum, it all means we're going to find critical values. CVs shows you that. So you always start with finding, step 1, find critical values. And now you're like, I don't remember what she's talking about. Critical values. They call critical because something critical is happening there. Two critical things are happening at critical values. Derivative is 0 or derivative does not exist. So reminding you, it's going to be the last time I will remind you this. From now on, you should remember. If I wake you up 2 at night, what are the critical values, Chris? And Chris is like, what are you doing in my room? The derivative is 0 or the derivative is D and E. Right?
I'm sorry.
It's like a stalking instructor. Yeah. So that is critical values. These values are important because they are candidates for max-min. Basically, any point can be maximum and minimum, but we don't have time to check infinitely many points. Who will do that? Even computers cannot do it. Thus, mathematicians were smart enough to shrink the list. Where we should look? In the darkness. How will you find things when it's dark? The mathematician says, let's find where derivative is 0 or D and E and only check these points. If none of them are maximum minimum, then you don't have any. So it's nice that we made a list smaller from infinite long list to just critical values. And I call them CVs. CVs. Just nice notation. Critical numbers, in some books, CNs, and critical points, CPs. It's the same thing. Books did not agree how to call it. The moment you see critical values, that is a synonym of derivative. So let's find a derivative. F prime that is a polynomial. You'll be very lucky to get this on a test. Now we don't usually put polynomials in a test. We put some kind of fractions to torture students. 4 goes down, 12x cubed minus 6 goes down. What is that? 13 times 6. 48x. No? 16 times 3?
Yeah.
48. Plus
13 times 6. Sorry.
Plus 9. 9 gives you 0. Put this in the box. We will need it. If you missed the class last time, you don't know why. But maybe you remember, when we build a sign line, we will have to use this formula. So boxing or circling your answers will be pretty convenient for you. Like when I'm zooming out my work, look what we did last time. I'm zooming it out, it looks like this. How can you find anything here? Because I'm boxing my answers. Whatever is important, I'm putting in the box. So if I need to refer to it later, I can see it now. And I trained myself doing it when I was a student in college. And color coding also is a cool thing. I was doing different colors. That's actually a part of your memory. Helps to color code. And I personally did theorems in red, properties in blue, definitions in green. So these things help you to find things in the future. Unless you're colorblind, of course. Now, 2 things. Step 2. I need to check where this is 0 and D and E. Called 0 points and singular points. You don't have to memorize that. But basically good points and bad points, both are needed. Because maximum can be looking like this, or maximum can be looking like this. Sharp corners, the derivative there does not exist, but you still have to check that. That is also maximum, So don't discriminate maximums just because they look ugly. So let me factor out 12. And then I will have even x squared, why not? Factor out, it will be x minus 4 equals to 0, or D and E. Since this is a polynomial, that's a nice abbreviation for polynomial. Polynomials don't give you D and E points, they are continuous, no matter how high the power. Polynomial of 11th power just gonna wiggle 11 times, but it doesn't break, so it doesn't have D and E points. Fractions do. We're going to do a fraction today. But the numbers are fine. Sine, cosine also is fine. Does not have any breaks. So we only look for zeros. And then this poly name, no D and E points because it is polynomial. That is why. But polynomials do have zeros almost all the time. How to find zeros? Factor out and then set equal to 0, each factor, because either one of them or both give you 0. So you have 12x squared equals to 0. Welcome to pre-calculus class. X minus 4 equals to 0. Hope you remember this. But if not, I'm reminding you. X squared equals to 0. X equals plus or minus 0. This is a dumb thing to write down, but I want to kind of make a memory of yours that don't forget. If you have square, you should put plus minus. It's 0. And x equals to 4. Put this in boxes. These are critical values. You found them. 2 critical values. Well, 3, but plus minus 0 is just 0. So 2 critical values. Step 2, you found critical values. Now all the answers will come from that. Step 3, you perform first derivative test. First derivative test. And we did it last time. I just never mentioned or actually stated that this is called first derivative test. We are testing our critical values. Why it's called test? Because we're testing candidates, which are critical values, to be maximum or minimum. To do that, you draw a sine line, just like we did last time. Sine line for the derivative. That is important because soon we're going to do sine line for the second derivative, actually on Monday. So I'm drawing a sine line. And I personally put this notation here. Not all professors do that, but that's my notation. Sine line for the derivative. That indicates, it reminds me where to plug my test points later into derivative. I'm putting my critical values in order. One was 0, one was 4. It is called sine line because we need to check signs on each interval. How many intervals do you see?
Or 3.
3. There's a theorem which we don't teach you because it's not a pure math class. In a pure math major class we teach, there's a theorem that says choose one test point on the whole interval, in this case from minus infinity to 0. If that one test point, random point, gives you some kind of sign, plus or minus, the whole interval will have this sign. Then, same thing with the second interval. Choose any test point from 0 to 4. That test point gives you a sign. The whole interval will have to have the same sign. Finally, the last one is the orange, and so on. Orange, I said? Okay, good. So, that's what you call testing the sign of each interval. That's why we call it sine line. Sine line. Plus, minus, plus. I don't know what's going to happen. Up, down, up. Let's see. Choosing a test points. Choosing test points. And that is why your homework and exam not process will be different from other students because it's a creative process. From minus infinity to 0, what kind of easy point you want to choose as a testing point? -1 is definitely a very good choice. I like doing minus million, I mentioned last time. I like doing huge numbers because A, it's fun, and B, remember, where do I plug them? So I have lots of stuff written here. Where do I plug my test points? Original or the derivative? That's a good question. The derivative. And that's why I call it sine line for the f prime. Plug into derivative. And that's why it's called sine line of the derivative, or for derivative. Because if derivative is positive, the original function is increasing. If derivative is negative, it's decreasing. That's why I showed you this beautiful picture and the ducky traveling, right? So, test points. The first test points we chose x equals -1. That is good. Any is good, to be honest. Just it should be on the interval. Nothing outside of the interval. -1000 also is good. Go here and plug it into the box you see. You can plug it into the factored form, but I don't recommend you. Usually students do mistakes when they do. So remember, I don't care the number. I need a sign. That's what we call a sine line. 12 times minus 1, minus 48 times minus 1. What do you think? It's positive or negative?
I think this whole thing on the screen. I think it's going down a bit. I can't see any of it.
No, minus 1. I'm plugging here.
Oh, I thought you were writing things down.
I'm plugging minus 1 over here. What do you think? I don't care the number. Plus or minus as the answer. What do you think?
Minus.
I think it's minus. And that's why I like choosing huge numbers, to be honest. Because if it's a million squared times minus 48 will be bigger than a million cubed times 12. So you're like, yeah, it should be negative. Or you can check. Minus 12 minus 48 gives you something negative. And I don't care what negative it is. So, f prime of minus 1 is negative. You see, you should learn. This is the first experience in the math class that tells you what is important and what is not. You should learn slowly what's important in STEM and what's not important. The number here is not important. Nobody will care to know the test numbers. What's important is the sign. So, if derivative is negative, I will put a sign here, minus. What is the original function doing? F.
Going down.
Going down. What's the terminology for going down? Decreasing, thank you. Decreasing up until 0. So now we know, that's why you're doing it. So the derivative is negative, means the original is decreasing. Remember, the duck is going down. Now, second interval from 0 to 4, what test point would you choose? Let's choose like 3.17. No, I'm joking. That's like, don't choose weird numbers. Choose something simple and fast. 1 is good, why not? But again, I'm wanting to make a point. It's very creative. Choose whatever you want. And now with your calculators, when I was taking this class, we're not allowed to use calculators. So that was important to choose a good number. In your case, choose anything you want. Plus or minus? I don't know, I'm going to the box. Where's my box? Here it is. I'm plugging 1. 12 minus 48 definitely is negative. All agree? 12 minus 48, something negative. So I'm putting minus again. If the derivative is negative, the original function f is going down again. So it's keep going down after 0. That means 0 is neither local maximum, not local minimum. The function was going down, and it was keep going down. And soon I will show you the graph, what it means. So that is already an information we have. It is not a maximum, not a minimum. We have last interval to check. So that we did 1 over here. Last one from 4 to infinity. Would you like to choose something like a million for fun?
Sure.
10. 10 is also good because it's like, why not? Let's do 100 just for fun. So I'm going back to the table and I see 100 cubed will have like 6 zeros times 12. 100 squared will have only 4 zeros. So the first thing is bigger than the second thing. That means the answer will be positive. Do you see what I mean? Like, it's nice to do huge numbers because you see the pattern. But you can do 5, 10, anything is fine. Derivative of 100 is positive. So the original function is going up. What is the terminology for that? Increasing. Now visually, the first derivative test, which I copied here, I'll go back in a second, just a second. Nope. The definition of the first derivative test says, if you go from plus to, yeah, I know it's gonna happen. If you go from plus to minus, that is, let's see, go down, go down. I know you are tired. It doesn't like to have 2 lectures in a row. Sometimes I give 3 lectures in a row and then it gets very needy. Okay, good. Go, baby, go. Yes. So some professors force you to remember, oh, from plus to minus, it's a maximum. From minus to plus, it's a minimum. Too much to memorize. Visually, just makes sense. Going down and going up. That is minimum. Right? Maybe it's the smallest minimum, then it's a global minimum. In this case, we don't know, so let's call it local. It's a local minimum. 61 should be fine. So, let's answer the question. The first question, A, asks us, find the intervals of increasing and decreasing. First derivative test answers this question. This is very visual, and the way I teach it is like very visual. Now you know where your function is increasing and where it's decreasing. You're literally just showing it up and down. So, looking at this, can you tell me f of x is, let's do decreasing first. Decreasing, interval notation. Where does it start decreasing? You see, you don't have a graph of the function, but you have a first derivative test.
Negative infinity.
Starts from minus infinity, and now it goes down till? So it's a good question, till 4 or till 0. And then there are different discussions about this, and the mathematicians around the world agreed not to merge those two intervals. We have justification about this. It's 0. It is neither decreasing nor increasing. So kind of, we're not supposed to equal it. We're supposed to go from minus infinity to 0, and then from 0 to 4. At 0, the point stopped increasing or decreasing. It just flat, and then it's keep going. And it looks, I will show you soon how it looks like, so you will have a visual. So we will indicate the breaking point 0, and then it was keep decreasing from 0 to 4. Decreasing, decreasing. Like so. On the graph, so we will do increasing. Skip some space for minimum and maximum, but I want to start showing you the graph. It looks like so. The function was decreasing, decreasing, and then at 0 it's kind of stopped decreasing. It became horizontal. Sometimes we call it horizontal tangent. But then, instead of going up, it decided, you know what, let's keep decreasing. So it was keep decreasing. That's what it means. So it was decreasing, and then it was decreasing again. Now, where does it increase? Do you see? From 4 to infinity. Great job. From 4 to infinity, the derivative was positive. So from 4 to infinity, it stopped. See, just like here, it stopped here. At 0, the graph stopped, but then keep decreasing. But then at 4, it decided, you know, let's increase. And that is the sketch of the graph. So, increasing, decreasing.
Wait, why did you write B for that? I thought B was finding the extrema.
No, it's a graph, I know. It's like just a graph. I want to show you the graph first. You're right, he is right. B asks to find local maximum, local minimum. So, local max and local mean point. Okay, let's do not point yet. There are two types of questions, point or value. So, x equals, where is a local maximum? What do you guys think? Everyone, what do you think from this sketch?
There is no.
So it was going down, and it was going down, and it was going up. First version, there is no local maximum. How about anything else? What do you think? There is no local maximum, exactly, because it will always increase from the left, decrease to the right, but goes up on the left. And as you can see, it was never a change. I forgot to put plus. There was never a change from plus to minus of the derivative. So we will say none. None for maximum. There is no such a point. Yeah, it's fine. Parabolas, for example, they either have one minimum or one maximum, so that happens quite a lot. For the minimum, though, we do have x that gave us minimum. Which one? 4. 4 on one of those two candidates for local max and local minimum, and 4 end up to be local minimum, while 0 end up to be not anything. So 4. Now we need to find f of 4 to see how low or high that relative extreme value it goes. So that means I need to plug plug into original. At the end, you always do the same step at the very end. You want to know how high or how low that point is. And it means you're plugging into the original. The original function is 3x to the 4, 4 to the 4, minus 16, 4 to the 3, plus 9. So, carefully calculating, that gives me...
-247.
Oh, thank you. That was fast. -247. That's what I have in my notes. Do you have my notes or something? Good job. So, nice. That means this pit is -247 units low, whatever it is, feet and meters and so on. So here's the idea. Here's the sketch of the graph. This is 4. This is 0. At 4, we do have local minimum. Local, which is actually a global minimum as well, but we're gonna learn them on Monday. It is the smallest point of the graph, so it is both local and global. And it goes as low as -247 units. At 0, though, yeah, actually that's true. If you plug 0, you get 9. Good point. 9. It's neither maximum, not minimum, and sometimes we call it horizontal tangent, which is not an international terminology, to be honest. Sometimes we just don't call it in any way. Let's see if we have it in our book. Nah, not really. But sometimes they call it horizontal tangent. The derivative here, I will zoom in. The derivative here is still 0, and derivative here is 0. For you to understand, let me put this here. The derivative is 0. It was a critical value. The derivative is 0. But this is a good example when the critical values are only candidates. They not necessarily give you maximum or minimum. Sometimes the function is going up, stopped, and then goes up. So then it's not minimum, not maximum, like a chair. Questions, what do you think? This is a very typical written problem on the test. As you can see, it has lots of steps and it's not too bad. Did you check everything? Check twice, no?
That's good.
Good job. But Luz, I need you to fill in, can you fill in this table?
Yeah.
And your name. Thank you. So, that was a good example. Let's do something with fractions, because that freaks you guys up. Example 2. What if a function f of x is looking like so? This is a very classical example. 2/3 x minus 2 raised to the 1/3 minus, oh no, sorry, that is already a derivative. A function is x minus 2 raised to 2/3, thank you, plus 1. Let's do the same thing. It's always the same question. In the future, we're going to call this question analyze the function. And an analysis of the function, say this function represents biological experiment with mice in the lab. You know, we do put like tumors in the brain of the mice. Like, it's actually very interesting. Slice the brain to see what is happening. So all of these functions, they represent something. Find where it's increasing, decreasing, where the medication is increasing, decreasing. All this starts with the very first step. Use the first derivative test, which starts with finding critical values. Finding critical values means find a derivative. Who was not too bad at the first exam and remembers chain rule? How do we do that? Who knows? Tell me. What is the derivative of this? You guys should know, we just took the test.
2/3 x minus 2 to the negative 1/3.
Negative 1/3 times the derivative of the function inside, but by the good luck, it's just 1. Good job. And plus 1 gives you 0, right? Plus 1 derivative is just 0. All agree? That's the derivative of the function. Put it in the box. Remember, we need it. Okay, so we got this. This should be checked for zeros in singular points, which are D and E's. Doesn't really look nice. I don't understand how to solve this. So usually I recommend to rewrite it as a fraction to see what is in the numerator and what is at the denominator. So let's keep writing it. 2/3. 1/, because of this negative sign. So 1/, x minus 2, and it is a cubic root, but to be honest, you can keep it as 1/3. That is fine. So put this also in the box. That is also a good one. It's the same thing, but written as a fraction. Now, remember this. This is important. Zeros are coming from the numerator. D and E's are coming from the denominator being 0. So, again, these will give you D and E points. Numerator equals 0 gives you good points. Denominator equals 0 gives you D and E points, which makes sense. And that's what we're going to do right now. Yes?
Since you said earlier it was a chain rule, why don't we multiply that derivative by the derivative of x minus 2?
We do. Derivative of x minus 2 is 1. So I just did not write it. You're right. I could times 1 and plus 0 also. It's like how detailed you want to write it down. Good question though, because it's a catch in your homework. You will have 2x minus 2, and then that's chain rule. Good job. So, the numerator is 2. Okay, 2 times 1, to be honest, equals to 0. The denominator is 3 multiplied by x minus 2, 1/3 equals to 0. Both should be checked. The derivative, where derivative is 0 and where derivative that does not exist, these points are called critical values. They are critical because they might give you maximum or minimum. For the first case, what would you say for that case? Does not exist. There's no solutions for that. BS. no solutions. 2 does not equal 0. So no, that does not work. What the heck? No solutions here, but sometimes you will get solutions. The problem will be just too long. I will do this example next week when we have solutions from both numerator and denominator. From the second one, we will have something. Divide by 3. X minus 2 raised to the 1/3 equals to 0. Raised everything to the 3rd power. X minus 2 is 0 to the 3rd power, which is 0. X equals 2 is a critical value because the derivative there does not exist, but it's also because it's in the domain. So I will write down the note. X equals 2 is the critical value because, BC, the derivative at 2 gave me D and E, and it's also in the domain, and X equals 2 is in the domain. In the domain, like so. The domain thing may be a little bit confusing for you, but the thing is maximum and minimum cannot happen in the vertical asymptotes. You kind of have to understand that. If there's a function and then there's a VA, it's not a maximum or not a minimum. So we do not choose the points. The function there is D and E, the derivative there is D and E, but that's not maximum and not minimum. That is why to avoid situations like this, we better have points which are in the domain to avoid the vertical asymptotes. That's the idea. And gaps in general. So now we do the same thing with a sine line. Let's do the sine line. Draw the sine line. So was it step A or 1? It was step 1. Step 2, sine line. Sine line. Oh, perfect. We're gonna finish right on time. Remember, sine line right now for the first derivative test gives you a sine line for the first derivative. I'm saying it not just for fun. Soon we're going to have sine line for the second derivative. So remember, first derivative test, increasing, decreasing. That is about first derivative. Soon we're going to have concavity, concave up, concave down and stuff. That is second derivative. Put all your critical values on the sine line. We have only one, which is called 2. X equals 2 is here. Check this sign. I need to plug into the first derivative some kind of test points. How many intervals do I have? 2. So we only need two test points. Choose. Which one would you choose from here? 0. I would choose 0. Yeah, negative also good, but honestly 0 is the best thing ever. Unless 0 is in the list of critical values, then you cannot choose it. But choose it if you can. That's the best thing to choose. Plug 0. Where do I plug it? Into the box. Where is my boxy box? Here it is. Either the first one or the second one, whatever you prefer. I don't care about the number. Remember that. I care about the sign. 0 minus 2 gives me negative number. And now what matters is what it is raised to. If it's raised to square or 4, it becomes positive. But in this case, it's raised to the 1/3. 1/3 keeps it negative. Multiplying by 2/3 keeps it negative, so the result is negative. So you see, that's what makes you kind of smart when you skip all the extra steps and you just need to know the sign. It is negative. If you want, I can write it down for you if you want. Maybe for this just one case. 2/3 over a cube root of -2. It is negative. That's what I mean. So let's put minus here. Now we know that the original function, so minus is about the derivative, but the original function in green is decreasing. Nice. What's the second test point you want to choose?
3.
1,000. I like 1,000. Oh, 3 is a good choice. Because you have 1.
3.
I kind of like 3. Good point. I like thousands because I just like it. Sorry. But 3 is a smart choice because then you will have 3 minus 2, which is 1. 1, whatever you want to do with it, will be still positive, unless you multiply it by the negative numbers, of course. So immediately done. But 1,000 is also good. 1,000 minus 2 is positive, so nice. Then it's plus, and in green, the original function is increasing. Look at my sketch. The function was decreasing because derivative was negative. Then at 2, derivative is d and e, and now the function derivative is positive, so the function is increasing. This is a local minimum. So, step 3. The original function f of x is increasing, decreasing. Increasing from what to what?
Infinity.
I keep changing on purpose so you don't get confused. Be careful. Increasing, going up.
Sorry, from 2 to infinity.
From 2 to infinity. All agree? So going up. Now going down from infinity to 2. Don't include endpoints because at 2 it's neither increasing nor decreasing. It's actually d and e there.
Infinity ain't doing that.
Yeah. The original function f of x, the original one, you see, has no local, which ones? Maximum or minimum? Look at the graph. No local maximum, nice. But it has a local minimum at x equals 2. X. Yeah, I know, baby. A little bit more. You can do it. At x equals 2, plug 2 into the original. At x equals 2. Plug 2 into the original. F at 2 is the very, very original. Will be 2 minus 2 raised to the 2/3 plus 1. Oh, that's a very nice convenient number. It gives you 0, right?
Plus 1.
Oh, plus 1, sorry. That's a good point. Oh, I did this mistake on purpose, so you catch it. So the point, actually, so maximum, local maximum has annotation 2, 1. Yes?
Wouldn't actually that input not exist? Because 0 to the 2/3 would be 2 over 0.
No, good question. Minus 2/3 will be over 0. 0 to the 2/3 will be 0 squared, third root. Minus 2/3 will not exist. Good question. Good question.
I forgot how it works for a moment.
Good job. Good job. Finally, this catch. Do you know how it looks like? Since the derivative did not exist, it was a cusp. It's a sharp corner. The function was decreasing and it was increasing with a sharp corner which gave d and e for the derivative at the point 2, 1. And that is my local and actually global minimum. Isn't it pretty cool? So we did found the local minimum, even though it's a sharp corner cusp. And that's kind of what the homework looks like. Exam will look like that too, yes.
Well, wait, you said it has no blocks?
Oh, yeah, sorry. Good catch.
Wait.
This is supposed to be minimum. Thank you. Minimum, yes. Yes.
Do you need to assign new stuff today, or some of the stuff you assigned last class that was due today?
I think we covered everything, so now you can do it.
No, I asked. I'm sorry. You assigned some last class. Yes. Sunday. And I don't know, did you assign more, or? Well, I'm going to decide more, because I already did that after, yes. And I wasn't sure if there was another one. I'm going to double check to be sure that I'm sorry.
Double check if you're right.
Some too hard.
You will love it, yes. Yes, let me stop recording. Come on.